Okay, so let's look at an example here. What we have here is a third order filter, and we can tell it's a third order filter because we have one stage here, a second stage, and a third stage. Now, this problem is just asking us for what is FC and what is F3dB. And this is actually just a pretty straightforward problem here, because since we have R1 equaling R2 equaling R3 and C1 equals C2 equals C3, we would get that F sub C is 1 over 2 pi RC. So if we do that, that'd be 1 over 2 pi times 1k times 2.2 nanofarads. And let me just do that real quickly. And take the inverse of that. I get 72.3 kilohertz. Now remember, this is not my minus 3 dB point. In fact, this should be my minus 9 dB point. But now, if I do here to do F3dB, remember we had a formula for that. That's just equal to F sub C square root of 1/2, I'm sorry, not 1/2, 2 to the 1 over n power minus 1. And so if we do that computation, we get here 72.3 kilohertz times 2 to the 1/3 power minus 1. So I'm going to pause to do that computation. And when I go through those computations, I wind up with 36.86 kilohertz. Now, the story behind this kind of filter is actually more than just this, because we made an assumption, oh, I can make these all equal and I get the same cutoff frequency. But if we actually go to a circuit simulation, we don't get that. Let me show you. Okay, so I've built the circuit here in the circuit simulator, showing here, I've got extra wire I don't need there, with the 1 kilohertz or 1 kilo ohm capacitor, 1 kilo ohm resistors, 2.2 nanofarad capacitors, so on and so on. And I'm just looking at the dB and the output there. So I'll go ahead and run this simulation. And as far as my simulation profile here, if I look at the simulation profile, there we go. You can see I'm going from 10 hertz to 1 meg, and points per decade as I'm doing 50. Alright. And we can see, yes, this is, well, you can't see it because you probably see just a blank screen right now. So let me resize this so it goes into the recording window. And it somewhat resized. Why didn't it completely resize here? Let me see if I can just do this here. There we go. So here we can see, yes, it's a low pass filter. We got everything good here. And then I've already done some evaluating some measurements on the simulation before. And you're probably, depending on the quality, you're probably not going to be able to read this. But in fact, I'm almost guarantee you can't read this. But we get here that the minus 3 dB point is 14 kilohertz. So I'll write that on the OneNote here. Simulation gives minus 3 dB at 14 kilohertz. Well, that's way off from what we said it should be. We said that the 3 dB point should be 36.86 kilohertz. What's going on here? Well, we made an assumption we made here, which was a very bad assumption, quite frankly, was that essentially these stages act independently. In the sense that this is kind of just isolated, gives me minus 3 dB. This is kind of isolated, gives me minus 3 dB. And this is kind of isolated and gives me minus 3 dB. But the issue is this 1 kilo ohm resistor here is actually, if we look at just kind of this first stage as a block, there's a 1 kilo ohm resistor here, and that resistance is going to be a load on this filter. That load is going to drop the equivalent resistance to 500 ohms. So just on that first stage, we're actually dropping that frequency because our REQ is not 1 kilo ohm, it's actually 500. And then we have to kind of do the whole thing there again. So you might say, well, how could our equations be wrong here? Well, it's having to do with a loading effect of these that we didn't account for. But there's an easy way to fix that. Instead of letting R1 equal R2 equal R3, we scale these. So if we're going to let this first stage here be 1 kilo ohm and 22 nanofarads, to reduce the loading effect, since I'm looking at the resistors in parallel, let's just make this bigger. So I'm going to make this 100 kilo ohms. But if I make that 100 times bigger, I've got to make this 100 times smaller. So that would be 22 picofarads. Now that's going to take care of this component loading this first stage. But now this 1 kilo ohm resistor is loading this 100 kilo ohm resistor. So how do I take care of that? Well, I need to make something much bigger than 100 kilo ohms. Okay, well then I'll go ahead and make it again 10 times bigger, but that means I got a 10 mega ohm resistor here, and this then becomes a 0.22 picofarad capacitor. And let's go ahead and do the simulation on that. So let's change my simulation here. So this is 22 picofarad. This is 100K. One meg or 10 meg. Oh, wait, this is still supposed to be 2.2 nanofarads. It's this one here that's 22 picofarad. And then this becomes 0.22 picofarad. Okay, so then we run it. It looks like the same graph here. And then if I evaluate my measurements again, turn those back on, again you probably can't see them here. I actually have to like squint my eyes to see them too. We get 36.42. So now trying to avoid loading effects, we get 36.42 kilohertz. Well, now that matches this here. So it's not that our equations were wrong. Our equations were correct. It's just when you match like this, you're going to have loading effects. But it's not really the end of the world. You can always, design letting them be equal to each other, and then just like we did up here. So we designed the filter so that they're all equal to each other, and then we just scale the stages. But this also indicates a problem with these kind of passive filters that we have. Because if I want to avoid those loading effects and adding more stages here, I'm already getting at, just at a 3-stage, I'm already getting at values that just don't make sense as far as realistic component values if you're talking about a circuit board. 10 mega ohm, yeah, you could find a 10 mega ohm resistor, but 0.22 picofarad, yeah, you can find a 0.22 picofarad, but now you're going to be running into problems of, what about your traces and stray capacitances? Because 0.22 picofarad is a very small capacitor. So we're going to be running into other parasitics that you'd have to take account for. So, and then if you added a fourth stage, now you're talking about a 1 gigaohm resistor. That, I'm sorry, not a 1 gigaohm, a 100 mega ohm resistor. No, wait, no, it was a 100. No, it would be a 1,000 mega ohm resistor or 1 giga ohm resistor. And now we're talking about 0.22 femtofarads capacitor, which is just unrealistic to have. Now, as a simulator, we can always simulate it, and the simulator just is a number cruncher, and so it's going to say, yep, it works. But if you were to try to build that circuit, like if we were trying to build the circuit on a breadboard, probably would not get the results that the simulation were giving us, because there's all sorts of stray capacitances in those breadboards. All right, but it is something interesting. Now, let's talk about high-pass filters. And this conversation is going to be very short. High-pass filters. Well, so on and so on. C1, R1, C2, R2, so on and so on. And these give us high-pass filters. And there's not much to talk about here. The cutoff frequency would be 1 over 2 pi, and it's really not the square root, it's the nth root, and n is the order of R1, C1, R2, C2, dot dot dot, Rn, Cn. Or if R1 equals R2 equals dot 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 Rn, and C1 equals C2 equals dot 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 Cn, then Fc would just be equal to 1 over 2 pi Rc. Now, omegas I didn't write there because the omega, all you do is you get rid of the omega c here. You just have 1 over, come on, there we go, nth root of R1, C1, dot dot dot, and then omega c equaling 1 over Rc. So, if they were all equal to it. Because again, all you're doing is getting a factor of 2 pi disappearing. And then the 3 dB is the same thing here, where we have the square root forgot here, Fc square root of 1, not 1, 2 to the 1 over n minus 1. So same formulas, because all we're literally doing is flipping components here. So that's all there is to talk about high-pass filters. I'm not even going to do an example. You just have to be able to identify by looking at the circuit whether it's a high-pass or low-pass filter, or by looking at the transfer function.